This is our last section for week 6, and it's going to be a really short one. Just going to look at a couple exponential models. We have principal for compound interest. For principal P invested in it, it's either invested or borrowed if you're talking about a loan. But for principal P invested at an interest rate R for T years, the new balance A is A equals P times the quantity 1 plus R over N, all raised to the NT power when it's compounded N times a year, and A equals P to the E to the RT power when compounded continuously. So a total of $10,000 was invested in a college fund for a new grandchild. If the interest rate is 5%, how much will it be in account in 18 years by each method of compounding? So on part A, let's write my principal is $10,000. My interest rate is 5%, but we're going to call it 0.05, not percent. We're just going to, anytime we do anything mathematically with a percent, we use a decimal. And then T is 18 years. So let's look at quarterly. So there's 4 quarters in a year. If I forget about that, I think of how many quarters are there in a dollar, and there are 4. So N here equals 4. And I'm going to write A equals going to use this right here. So 10,000 times 1 to the 0.05 over 4 to the 4 times 18, which gives me 10,000 times 1.0125 to the 32 power, which gives me $24,459.20. If I do it monthly, now it's N equals 12. And I get A is equal to 10,000 times 1 plus 0.05 divided by 12 to the 12 times 18, and that gives me 10,000 times 1.0042 to the 216th power, or $24,550.08. And then, oh, my handwriting's terrible today. And then continuously we use A equals P to the E to the RT, or as I used to always call it, A equals PERT. So it would be $10,000 times E to the 0.05 times 18. And so I would put that $10,000 E to the 0.9, or it gives me $24,596.03. So as you can tell, the more compounding you have, the more money you have. It may not be significantly more, but you do have more. Could be based on how much initially you put in, though. Okay, so other topics that are modeled by exponential functions involve growth and decay. Both use the general formula A equals PERT. We use for growth of money, except for growth and decay, generally use we call it A sub 0 or A naught. NAUGHT, as in nothing, or A sub 0. That's when time equals 0, or the original amount. That's always A naught, or A sub 0 is always your initial conditions. So we call it A naught instead of P. We see that exponential growth rate has a positive growth rate and decay is a negative decay. So if I have, for our original amount A naught that grows or decays at a rate R for a certain time t, find the amount A is A equals A naught e to the RT. So Chris is a researcher at the Center for the CDC, and he is trying to understand the behavior of a new and dangerous virus. He starts his experiment with 100 of the virus that grows at a rate of 25% per hour. He will check back on the virus in 24 hours. How many viruses will he find? So we have A equals, so he started with 100. So A naught is 100. I should be better about that. Okay, and time is 24 hours, and the rate is 25%, which we have to use 0.25. And so that gives me E to the 0.25 times 24. And then when I put all this in my calculator, I get 40,343. So in one day, you go from 100 to that many. All right, here's some other applications here. We just did exponential growth. That's really all you need for your homework, but if you're interested in these other ones, there's neat videos you can watch.